Have you ever been sitting at a stoplight, seen a self-driving car just glide by and thought, how does that thing actually see? How does it make any sense of the absolute chaos of traffic and people and roads? Well, today, we're going to pull back the curtain and take a look at the incredible sensory world of an autonomous vehicle. So let's get right into it. It all starts with this one really powerful number, 95%. Now, at first glance, it's just a percentage, right? But this single figure, this is the key. It's the reason this entire industry even exists. It represents a huge problem that this technology is being built to solve. That's right. A whopping 95% of all traffic accidents are caused by us, by people. Little mistakes, bad judgments, moments where we just weren't paying enough attention. This is the fundamental problem that engineers are trying to fix. So the mission becomes crystal clear. It's not just about making a cool car that can drive itself. It's about engineering a driver that is fundamentally safer, more reliable, and way more vigilant than any human could ever hope to be. And to get there, a machine needs to do way more than just see. It has to perceive. It needs to understand everything that's happening around it with a level of reliability that honestly feels kind of superhuman. So how on earth do you give a machine senses? Well, before you can build the driver, you have to figure out the job requirements for its senses. What does good enough even look like? And it really boils down to a few key performance metrics. First up is range. This one's pretty simple. How far away can the sensor actually spot something? And as you can probably guess, the faster you're going, the more important this one becomes. Next is resolution, and this is all about seeing things clearly. So imagine you're looking way down the road. You see two headlights. High resolution is what allows the system to know for sure, hey, that's two separate motorcycles, and not just one blurry car. And that distinction, absolutely critical for making safe decisions. And that brings us to our third and maybe the most critical metric of all, accuracy. It's not enough to just see an object. The system has to know exactly where that object is. Is that car safely in the lane next to you, or is it drifting over into yours? The margin for error here is incredibly small, as this next slide is going to show you. This table really drives the point home. Look at that first row. A passenger car is about 1.4 meters wide. So the system has a little wiggle room, about 0.7 meters of allowable error. But now, look down at the pedestrian. They're only a quarter meter wide. The allowable error shrinks to a tiny 12.5 centimeters. Now imagine trying to be that precise with something that's really far away. It's a massive challenge. So, to meet these crazy demanding requirements, you can't just rely on one type of sensor. It's not going to cut it. Instead, engineers assemble a team of specialists, each with its own unique superpower. So let's meet the team. First, we have the camera. This is our team's visionary. Just like our own eyes, it's brilliant at classification. It can read road signs, see the color of a traffic light, identify lane markings. Its job is to tell the system what it's looking at. But also like our eyes, it has a major weakness. You throw in some rain, fog, snow, or just plain darkness, and it gets blinded pretty easily. Next up is our mapper, LiDAR. Now that stands for light detection and ranging. And what it does is it shoots out millions of tiny invisible laser beams every second, and then measures how long they take to bounce back. This creates an incredibly detailed, high-resolution 3D point cloud map of the world. It gives the system super precise shape and distance info. So what's its kryptonite? Well, it's traditionally been the most expensive part of the car. It creates a ton of data that has to be processed, and yep, just like the camera, it also really struggles in bad weather like heavy rain or fog. And finally, we have radar, the all-weather veteran. This is the reliable old-timer on the team. It uses radio waves that just punch right through rain, fog, and darkness. Its unique superpower is using the Doppler effect. The thing that makes an ambulance siren change pitch when it goes by, to instantly measure an object's speed. But its big weakness is low resolution. It can tell you something is there and exactly how fast it's moving, but it has a really hard time telling you if it's a car or a guardrail. So we've got our team, the visionary, the mapper, and the veteran. Now it's time to put them to the test in two very different, very challenging environments. First up is the highway. Now, this environment is structured, it's pretty predictable, but the speeds are just so high, and that raises the stakes a lot. This is the number that matters here, 134 meters.
On a high-speed highway, this distance is literally the line between a safe stop and a catastrophe. And that's because if you're traveling at 130 kilometers per hour, that's about 80 miles per hour, this is the absolute minimum distance your sensors need to detect a stopped object ahead, like a stalled car, to let the vehicle come to a complete, safe stop. This is a massive test for the range of our sensors. Okay, now let's completely switch gears. We're going to a totally different challenge, the back road. The speeds here are lower, sure, but the environment is infinitely more chaotic and unpredictable. I mean, on a back road, the challenges are all about complexity. You've got pedestrians, cyclists, animals that can just appear out of nowhere. You've got sharp curves that block your view. A lot of the time, there aren't even lane markings for the camera to follow. It's just a mess of frequent intersections and narrow roads. This kind of environment tests resolution and accuracy to their absolute limits. So, okay, we have a problem. The camera is blinded by fog. The radar can't tell a motorcycle from a pedestrian. And LiDAR is expensive and also struggles when it rains. Each one of our specialists, on their own, has a critical flaw.
Which brings up the obvious question, right? If every individual sense is flawed, how can a car possibly navigate the world safely? Well, the answer is, they don't work alone. The solution is this amazing concept called sensor fusion. This is the magic that holds the entire system together. It's the core philosophy. You take the separate data streams from all the specialists, and you weave them together into one single coherent and way more reliable picture of the world.
So let's see how this works. Imagine it's a foggy night. The camera sees this vague, human-like shape, but it really isn't sure. At the same time, the radar, which doesn't care about fog, gets a solid log. It confirms there's an object at that exact distance, and hey, it's moving at walking speed. LiDAR then adds the final piece of the puzzle, confirming the object's precise 3D shape. By fusing all that data, the car's brain has zero doubt that is a pedestrian. And the result is a safe, confident stop, made possible only because the team covered for each other's weaknesses. Which brings us to this one last thought. Our own human senses are deeply flawed. We get tired, we get distracted, we can't see well in the dark or in the fog. So the real question isn't just whether we can build a car that sees, it's whether, by combining these specialized, imperfect sensors, we can create a form of perception that is, in the end, far more perfect than our own.